The world around us is full of vibrations and waves, especially electromagnetic waves, such as heat and light. Among other electromagnetic waves are the invisible beams from radar antennae and the waves used for transmitting television pictures. Inaudible and invisible, they spread out like ripples in a pond. First, let us deal with the general principles of vibrations and wave phenomena. If a pendulum is moved out of equilibrium, then, when returning, it gathers so much momentum that it swings on. When a pendulum such as this moves to and fro once per second, its frequency is said to be 1 cycle per second. It remains 1 cycle per second until finally the motion dies out, mainly due to friction losses. If the pendulum is pushed regularly, it continues to swing, but the same fixed frequency is maintained. A shorter pendulum, however, moves faster. In this example, the frequency is 2 cycles per second. Other objects, such as this metal strip, vibrate still faster. Here, too, it is true that the shorter the object, the higher the frequency. The reason why we can hear these vibrations is that the air is set in motion. Sound waves are produced, which can spread over a great distance. All these phenomena occur, although in an entirely different form, in the electromagnetic waves used to carry the television picture. How are these waves produced? First, let us take a capacitor. 2 metal plates which contain, like any metal, innumerable free electrons. These negatively charged particles will move in a certain direction when an electrical voltage is applied. There will then be an excess of electrons in, say, the upper plate. Hence, this plate becomes negatively charged. Similarly, just as many electrons have been displaced from the lower plate, and, as a result, this becomes positively charged. Such a charge is accompanied by an electric field. Let us see how this displacement of electrons can be used to cause an oscillating movement. First, the addition of a coil is required. Here it is shown diagrammatically. It is also a conductor. The electrons from the charged capacitor will flow back and forth through the coil, and eventually oscillation will cease, so that the uncharged equilibrium state is again reached. Thus, there is a certain similarity between mechanical and electronic oscillation. However, here, only the electrons within the conductor oscillate, whereas in the case of mechanical vibration, the whole object moves. We will now consider how, by electron oscillation, electromagnetic waves can be produced. Let us look at the electric field. Here it is directed upwards, and when discharged, it will disappear. The current through the coil doesn't suddenly stop. The electrons swing back to the other side of the capacitor. Thus, the capacitor is recharged, and a new electric field, this time directed downwards, is produced. The electrons will then flow back again. In this way, the electric field alternates continually. Because current is flowing, a magnetic field forms in the coil. Here it is directed forwards. The field decreases proportionally with the current. Then the electrons flow back. The field reappears, but now in the opposite direction. Hence, the oscillation of electrons is accompanied alternately by an electric field in the capacitor and a magnetic field in the coil. As we've already seen, the oscillation dies out. This is partly due to electrical resistance in the circuit. The action, however, can be maintained by a regular supply of energy. In practice, this can be done electronically, by means of a valve or transistor circuit, to which the oscillatory circuit is connected, like this, or the other way round. Depending on the tuning, the oscillations produced in this way can have frequencies from less than 1 cycle per second to more than 1 million. The tuning is determined by the coil and capacitor values. A larger capacitor gives a lower frequency. A smaller capacitor gives a higher frequency. The same applies to the coil. Since in television engineering, frequencies of around 100 million cycles per second are used, the oscillatory circuits must be very small. Here is a simplified television transmitter. It is an oscillator which can set up very strong electromagnetic waves. These waves are radiated by a transmitting aerial, which is, basically, another form of oscillator circuit. In its present form, the circuit will not act as an aerial, since the alternating fields are confined within the circuit. As can be seen here, the electric field is concentrated in the capacitor. If this same circuit is given the form of a rod, however, it acts as an aerial. The electric field now extends indefinitely, as does the magnetic field. For the sake of simplicity, we will represent this field by just one line of force, and do the same with the electric field. The rod-shaped oscillator circuit is called a dipole. Here, too, alternation of the electric and magnetic fields occurs. But since both fields are rhythmically set in motion from the dipole, a wave movement is formed, which spreads out into space. The dipole's tuning is determined by its size. For a lower frequency, a longer dipole is required. For a higher frequency, a shorter dipole. So much for what happens close to the dipole. But what happens at a greater distance? Let us first consider the electric field at an arbitrary point in space. If the wave reaches this point, the electric field first increases and then decreases. It is then directed the opposite way and again decreases. This process repeats itself continuously, and so the electric field takes the form of a traveling wave. Now the magnetic field. As we've already seen, these lines of force are perpendicular to those of the electric field. The direction of the magnetic field alternates, first to one side and then to the other. Here, too, a traveling wave is created. The complete electromagnetic wave consists, therefore, of a magnetic component and an electric component, which, in space, reach their maxima simultaneously, whereas at the dipole they succeed each other. All electromagnetic waves consist of these two associated fields and are propagated in space at the velocity of light. The simplified representation here shows the relation between frequency and wavelength. At a lower frequency than this, the field alternates at a slower rate, with the result that the wavelength is longer. The part shown here contains exactly one complete field alternation, which corresponds to one wavelength. If the frequency is doubled, the wavelength is halved. Hence, each distinct frequency has its own fixed wavelength. Now we will examine the reception of these waves. For this purpose also, a dipole aerial is used. Again, for high frequencies, it must be short, and for lower frequencies, longer. What happens then within this dipole? The continuously alternating electric field exerts a force on the electrons, which move correspondingly. The accompanying magnetic field further increases this effect. We can say that the electromagnetic wave brings the electrons in the dipole into resonance. An alternating current forms, which can be indicated by a measuring instrument. Hence, energy is transmitted without any intermediate substance. However, this transmission is only possible if the aerials are correctly positioned. Where both dipoles are vertical, the electric field will induce a current in the receiving aerial. If the transmitting dipole is positioned horizontally, however, nothing is received. The lines of force of the electric field are then at right angles to the receiving aerial, and accordingly the electric field can induce no displacement of electrons, unless the receiving aerial is also set in the horizontal position. It will now be clear that the receiving dipole must always be positioned parallel to the transmitting dipole. To increase the directional effect of the receiving aerial, it is usual to add a few shorter rods at the front and a somewhat longer rod to act as a reflector at the back. Moreover, for practical reasons, the dipole itself is generally in the form of a rod folded double. The transmitting aerial usually consists of a system of different dipoles. To obtain radiation in all directions, a second set of dipoles is placed at right angles. Furthermore, through a combination of several of these units, the radiation can be concentrated in the horizontal plane. This is the electromagnetic wave which carries the television picture. It is therefore called the television carrier wave. We will now see how the picture is transmitted. In the television camera, an image of the scene is projected onto the sensitive layer in the camera tube. The principle of the camera tube is not dealt with in this film. For the moment, a brief summary will be given. The image on the sensitive layer is scanned electronically. In this way, the brightness of each separate picture element is converted into a voltage of varying strength. Since for the entire scene this scanning takes place very rapidly over and over again, the camera produces an uninterrupted and constantly varying signal voltage. This is the television picture signal sent out by the transmitter. Let us first consider a situation in which there is no picture signal. In this case, the transmitter emits a constant carrier wave. Here, the wave pattern is not shown, since the wavelength is relatively short. If there is a picture signal, the carrier wave is modulated. In other words, the strength of the carrier wave is changed by variations in the strength of the picture signal. This is called amplitude modulation, and in this way all the nuances of the television picture are transmitted together with the carrier wave. We now know what happens at the receiving aerial. In each dipole of the correct length, the carrier wave will cause the electrons to resonate, a resonance which in this case varies with the modulation of the carrier wave. Finally, in the television receiver, the original picture signal is regained. So we see how the picture signal, transmitted with the carrier wave, is finally converted into a luminous, live television picture.